Yep, that's me. Just a little more information for y'all on screen. There's my email address if you want to reach out to me. I'm on Twitter a whole bunch there. It's kind of my main way to interact with the community. I have a new blog, migrated it over to nosentino.com from my previous employer, Centino Systems, and also am Pluralsight author. Bunch of books published. I have a book published exactly on this topic that we're going to cover today, which is SQL Server and Kubernetes, which I published with my good friend and co-author, Ben Weissman. So please check out that. And let's get into it. Today is kind of, if you've never seen Kubernetes before, this is the session for you, right? We're going to start off and just discuss what Kubernetes is, and then the benefits of Kubernetes, like why are people doing this thing? And then at the end, we'll also talk about why Microsoft is investing so much in this. When we're talking about Kubernetes, we're going to write code to deploy systems. And what Kubernetes does is gives us an API to represent the resources that we want to deploy into our cloud or into our data center. And those are the API objects. And so we'll spend a bunch of time talking about those objects, which will become the building blocks of the systems that we deploy inside of Kubernetes. Once we understand kind of the how, not the how, but the what and kind of the objects and things like that, then we'll dive into the architecture of Kubernetes and Kubernetes clusters themselves. You can kind of know where these things actually live and breathe. Then we'll talk about deploying apps and then also deploying SQL Server. Or generally, when I say deploying apps, like stateless applications, and obviously SQL Server being a very, very, very stateful application. So that's what we're going to cover, and let's dive right into what is Kubernetes. Kubernetes is a container orchestrator, right? So I do kind of have the prerequisite of today, kind of like what a container is. We're going to jump right into what a container orchestrator is, but effectively give you the kind of the 10,000 foot view of a container. If you've never used one before, it's just a process running on a computer somewhere in a data center that has isolation boundaries built around it. And what a container orchestrator does is it figures out where to run a container inside a collection of resources or inside of a data center or inside of a cloud. So when I say a collection of resources, literally compute. So CPU, disk, RAM. And when I talk about pods, well, pods are an abstraction around container-based applications, right? So later on, we're going to deploy some simple hello world applications. That's going to be a container that runs in a pod that is scheduled to run on some computer inside of my data center. And that's really, I like to jokingly say, like Kubernetes has one job. It starts pods on nodes in a data center, right? Just literally just starts up processes somewhere. But there's some pretty advanced stuff that goes into the what and the where and the how of starting containers on nodes in a data center. The other big thing that Kubernetes gives you an infrastructure abstraction. And so I'm going to care a lot less about where or exactly where, like on what specific compute resource my process is running on in my cluster, because I'm going to treat that data center as it's the collection of resources and let Kubernetes figure out where to run that thing. Moreover, if I need networking, like a load balancer to publish that application out to the internet or to make it available to people, I don't have to get into the business of logging into my load balancer and configuring a load balancer and provisioning an IP and maybe logging into the whatever cloud portal I'm using to allocate those resources. I can just write code that asks the cluster to provision that for me, and then the cluster will interoperate with the resources in my data center to provision storage or to provision networking and things like that. Since we're going to be writing code to describe what our systems look like, we kind of know what that desired state of our application is, right? That's going to be what we write in the code. We'll describe in code what we want, maybe a collection of containers published on a public IP, and I tell Kubernetes to go do that thing. And what Kubernetes will do is make sure that we stay in that desired state. And we'll talk about how this works when we get later on in the session here. But the idea is I define the state. It's the cluster's responsibility to make sure that we define that state. And so what we're going to do is we're going to write declarative configuration in code. And so I'm assuming most of the audience comes from a SQL Server background. When I say declarative code, what I really mean is I just describe what I want, right? And as T-SQL folks, we're familiar with that concept. We just describe what we want in T-SQL. Select these columns from that table, right? I don't have to tell SQL Server to crack open that data file, to iterate through these data structures, to go pull off this particular byte stream. I don't have to do any of that. The storage engine does that for me. I just describe what I want in code, and it goes and happens for me by SQL Server. And the same concepts apply in Kubernetes. I describe what I want in code in the API objects that we'll talk about in a few minutes. And it's the job of Kubernetes to go do that thing in my data center. So what are the benefits of all of that? Well, workload placement. So I can figure out, given a collection of resources, where I'm going to run my workloads in my cloud or in my on-prem data center. I don't have to go and say, run this app on that server. I just say, run this app. And it's the job of Kubernetes to figure out where that is. It's the job of Kubernetes to also manage state, right? That desired declarative state that we described a few minutes ago. Just give me these things and then also keep me in that state. So if something goes wrong, Kubernetes actually has constructs to build self-healing applications. So if something goes bump in the night, a node crashes, a network partition, Kubernetes, given enough resources, can just move your workload to the rest of the cluster and get you back up and running without you having to interact with the system at all. Networking and services, I kind of described this a little bit. We're able to allocate and provision networking for access into our applications for things like load balancing. We can get for free out of a Kubernetes cluster some pretty basic load balancing for our applications, which is really interesting when it comes to scaling. We're going to see that in some demonstrations. We also have the ability to present persistent storage, super important to data professionals, and allocate storage, whether it be from cloud providers or other even on-prem storage devices. I now work at a storage company, and I have feelings about that, about persistent storage. And then obviously the declarative model, which I think we talked about that in pretty good detail, describing what we want to have happen in code. And so what we're going to do is, when we're talking about deploying applications into a Kubernetes cluster, let's kind of look at the high level what that really means. So a cluster is just a collection of resources. And then I'm going to come along and say, you know what, deploy these applications in code. And in that code, I'm going to describe what I want. So maybe I want a collection of web servers that are up and running backed by a SQL server. I can describe that all in code. What'll happen is Kubernetes will figure out where in the cluster to run these applications. It'll then provision network access to those and then keep these applications up and running. I'll have the code that describes what I want. I can take that code, stick that into a source code repository, and have that desired state affected in the cluster. If something goes bump in the night, Kubernetes can build self-healing constructs to make sure that I stay in this desired state. And we'll revisit this architecture here again in a few minutes. But how do I do that? Like, how do I describe what I want in the code? Well, that's where the API comes in. And the Kubernetes API is a collection of API objects that represent the resources that you want to deploy in your system. So really, this is the building blocks of your applications, right? So pods being your container-based applications. So pods is just an abstraction around a running container inside of a cluster. A controller is the thing that maintains the desired state. We're going to talk about deployment controllers and replica set controllers today as specific types of controllers. And each one of those provides a specific set of functionality when it comes to affecting the desired state in my cluster. And we'll look closely at what those are here in a few seconds. A service API object is what we're going to provision to get persistent access to our applications. There's several different types of services, some that are just inside of your cluster, some that expose your applications outside of your cluster, and some that integrate with hardware to provide load balancing services from things like clouds or things like F5 or Cisco devices that have to interoperate in on-prem data centers. Storage, which is going to be the way that we can provision and allocate storage. And these API objects here, so pods, controllers, services, and storage, really are the core building blocks to your apps, right? I have applications, I have a desired state, I have access to the applications with services, and if I have storage, then I have to have storage allocated for my app. And these are really just the basics. There's so many more API objects available to you to build more complex application constructs. These are really just kind of the basic ones when it comes to building systems. When I say systems, I mean application services and systems like that, not systems like networks and things like that, but just to clarify. All right, so let's talk about services and replica sets. So service is going to provide access to an app. A replica set is a controller that's going to keep my application in a desired state. And so let's say I have a cluster, which is just a collection of compute resources for now. In a few minutes, we'll describe more precisely what a cluster is. I'll create what's called a deployment. That deployment creates a replica set. And so those are two API object types. A deployment spins up a replica set. That replica set is going to have what the actual definition of the pod. So inside the replica set's code, which we'll look at in a few minutes, we're going to have code that says start this type of container, right? And what the replica set will then do when I tell the cluster to deploy this deployment, that replica set will go ahead and create the number of pods that I want to have up and running in my cluster, right? So the deployment is what I deploy. That deployment dynamically creates a replica set. The replica set has the definition of what I need to actually deploy, and then it stands up those pods somewhere in the cluster, right? I'll then front end access to that with a service. In this case, it's going to be HTTP, and that service is where I send users, right? And so I say, give me an IP address, give me a port. I'm going to send users to that service. That service is going to load balance the traffic to all of the pods that are a member of that deployment. And so here we have 4 pods. So as HTTP requests come in, they'll be distributed evenly across those 4 pods. So that's kind of like the very templated, very basic deployment inside of Kubernetes to get an application up and running. It's kind of the standard design pattern. Now, what a replica set will do, or a controller, which is a replica set is a type of controller, is let's say that pod crashes, right? Maybe the application died, maybe the node that it died, or node that it was running on died. What Kubernetes is going to realize is that my application is no longer in a desired state, because in the deployment, I said run this number of pods of this application, which was 4 in the scenario. Kubernetes is going to look around and be like, hey, there's only 3 pods running. What do you want me to do here? Well, automatically, it's going to destroy that pod or terminate it and then create a new one. And what's going to happen behind the scenes is the IP of the previous pod is going to get deregistered from the load balancer. When that new pod is allocated, it's going to get registered into the load balancer, and traffic's going to automatically start going to that new pod and being distributed evenly across the 4 inside of the cluster. That's pretty cool, because now you can build self-healing applications leveraging that construct. And so let's take this and extend it one notch further. So we looked closely at replica sets and deployments there, but let's see how they piece together and why a deployment doesn't create pods directly, right? So a deployment creates replica sets, which we learned a few seconds ago, and that replica set creates pods. And so let's say in that deployment, we defined a specific version of our application. So just V1, let's just call it that for descriptive reasons. We also will front end it with a service, and we'll send users into the load balancer into the service and get load balanced across the pods in that existing replica set. So let's say the development team comes out with version 2 of our application, and they're like, hey, Anthony, version 2 is out. It's available at this container registry and this new tag for the container. So let's say the tag is :v2, right, for the container. I'll make an adjustment to the deployment by changing literally one line of code. What'll happen is Kubernetes will sense that I've made that change. It'll create a new replica set in the cluster. And what it'll start doing is starting up the new version of my application in that new replica set. And that new application will get, or new pod with the new version of my application will start getting load balanced to immediately. And then I'll start shutting down pods in the old replica set, starting up new pods in a new replica set in an even way, such that we don't oversubscribe the resources in the cluster, and then shut down the remaining pod in that previous replica set. And so what we could do here is we get 0 downtime rollouts of our applications, right? So what we saw there is V1 was rolled out initially. I changed it to V2. V2 rolls out, and the load balancer automatically starts shifting the workload to all of the pods in the new replica set. And I then have a 0 downtime rollout. You might be thinking, well, what if there's a dependency on my application and I just can't do that type of rollout where it's real time? Well, there are ways to control the rollout such that you can shut them all down first and then start up all the new ones. But what you'll wind up doing when you start building your applications to leverage this type of technique is building your application so you kind of can have that 0 downtime rollout without having to have that big bang, shut everything down, start everything back up thing. And so that gets to be a very powerful construct when you're rolling out applications. So how do we do this, right? How do we get to that point where I can take those API objects, create some deployments, and get them deployed into the cluster? Well, we're going to write code to do that. And we're going to look at some code in the upcoming demos. But I wanted to talk about techniques before we get into the code. So imperative techniques are a way to deploy applications or a way to configure systems where you execute a series of commands, right? So start up this container, do this thing, provision that IP on this node over here, and I execute a sequence of commands to do that thing. That's great, but what I'm not left with when I do all of that is the configuration artifacts of what I want to do, right? I just executed a series of commands, and that could get lost in my terminal history and never seen again. Declarative techniques are going to be, I'm going to write code, I'm going to describe what I want, I'm going to check that code in the source code, and then deploy that later on in my system. And that's what I'm going to kind of push y'all towards when you want to deploy applications. We'll look at both techniques in the demos because I want to be able to show you how to interact with the cluster imperatively, but ultimately we're going to land on declarative techniques, writing code in YAML, right? Unfortunately, YAML. But Kubernetes speaks JSON. So when we execute commands, even though we're writing code in YAML, we're going to feed that into the cluster. And it's going to be converted to JSON inside of the cluster. So you'll see both used in a lot of different places. And so let's get into some demos. We're going to imperatively deploy a web application, and then we're going to access that web application inside of the cluster. And then we're going to look at some declarative techniques. So I'll make the code and the deck available for y'all on my GitHub repo. I'll have a link at the end of the session. And you'll have all of the shell scripts to describe what to do. You could build a cluster from scratch, or you can use any of the managed services that are available like Azure or GKE or Amazon. And if you are running Docker, let me show you one thing. If you're running Docker on your laptop, you're just a few moments away from having a Kubernetes cluster. And I want to show you where to do that real quick too. For some reason, Docker was not running my laptop, which is a very, very, very rare occurrence. So if you go into Docker on either Windows or Mac, I'm on a Mac here, and you bring up the Docker for Desktop window, unfortunately, my Docker client was stopped, so it's got to take a second to boot up. But if you look here on the left-hand side, you'll see a Kubernetes menu. And once I'm able to select this, which will be here in a moment, there's going to be a checkbox presented that says, there we go, enable Kubernetes. And so what you'll have after you install Docker and you check that checkbox is you'll have a Kubernetes cluster on your laptop, which is really awesome because then you can just go and run with these demos, or you can provision these in the cloud and things like that. So let's look at some code. So like I said, the first thing that we're going to do is we're going to start some workload imperatively. So I'm just going to execute commands to deploy workload. And kubectl is the primary command line tool that you'll use to interact with the Kubernetes cluster. kubectl talks to the API server, which is the core component of the cluster, which is the thing that's going to receive the instructions that you want to do inside of the cluster. So kubectl being the primary command line tool. So I'm going to tell my cluster to do something. I'm going to create a deployment named hello world, and I'm going to tell it to run this container image. This is a simple hello world application from the Google Container Registry, and we're going to run version 1.0. And so when I go ahead and I do this, what's going to happen is it's going to create a deployment in my cluster. All right. So if I do kubectl get deployment, so it's going to give me some information about a deployment, in this case, a specific deployment named hello world. We see that I have a deployment up and running. So hello world, one of one pods is up and running and ready. One is on the newest version of my application, and one is available. It means up and running and actually servicing requests. So I told you deployments create replica sets. Let's look at a replica set here. The replica set has a desired state of running exactly one container. It's currently running that one container and it's ready, right? Just describing the state of the replica set. That replica set created a pod. This is the actual container-based application that's running somewhere in my cluster. And so this is the name of the pod. So you see the name of the deployment here, hello world. This is called the pod template hash, which is a reference back to the replica set. And then it's, on the end here is just a unique identifier for this individual pod. It's running and it has 0 restarts. We'll look at restarts a little bit later when I crash SQL Server. So if I want to get access to that application, I have to define a service, right? So that's where I'm going to send users to. So kubectl expose, which is going to create a service for this particular deployment named hello world. I'm going to listen on port 80. So I'm going to receive traffic on port 80, and my container-based application is listening on port 8080. So I'm going to receive traffic on 80 and load balance it to port 8080 to whatever pods are supporting that workload inside of my cluster. So there we see hello world service is exposed. If I do a kubectl get service, I'll get the actual IP address of the service that's running inside of the cluster. If this was provisioned from an external load balancer, like if I was in the cloud or I had an integration with an on-prem load balancer, that address would be populated there. So I'm going to ask the cluster for this IP address and store it in this variable here. So that's all that's happening on line 27. So if I do service IP and I'll echo that out, we'll just see that I'm holding that inside of a variable here inside the cluster. So I'm going to use curl, which is the command line web browser, to access that service. So just imagine this would be users accessing my application. And this is just a simple hello world app running inside that hello world pod, hello world version 1.0. And it just prints out the actual host name of the pod that I got load balanced to. Since there's only one pod in the cluster, I'm just going to get load balanced to that one pod, right? Let's change that. Let's scale our application out. So kubectl scale deployment, hello world. I want to scale up to 3 replicas in my cluster. So a few seconds later, 3 pods are up running inside of my cluster. So just think, so 3 different containers got scheduled on the different nodes in my cluster. And those the load balancer got updated with the new pod IPs. And so now when I send traffic in, I'm going to get load balanced across those pods. So 4L SGB, VXD, J6, it's distributing that workload to the pods running in the cluster. We could see I have 2 pods running on node 3 and 1 pod running on node 1. So if you think about what we did there, just from a coding standpoint, I ran a couple of imperative commands and I got a workload running in my cluster. I have it publicly accessible and, well, more precisely, accessible within my cluster. And I scaled that application with a couple lines of code, right? And so that's really the power of Kubernetes, is rapid deployment and affecting rapid change. Because if I had to deploy 3 web servers and start up 3 different web applications on virtual machines, we're definitely not getting it done this fast. So let's say the development team produces a fantastic new version of Hello World 2.0, right? So they receive them going to change the image of the application to a new version of an app. So Hello World 2.0 comes out, was the kubectl set image for my deployment, Hello World. I'm going to change the container image 2.0. So we see the tag at the end. So run that code. It's going to tell me that it updated the image. If a few moments later, we're already in the desired state. So up to date means it's already swapped out the 3 containers and the 3 new ones are up to date. If I go ahead and I hit that service IP again now, we'll see I'm on version 2.0 and I'm getting load balanced across pods in the cluster. So imagine being able to do that, right? In code, your developers commit a new container image. They're like, hey, it's time to roll a new container image out. You update a configuration, you roll that code out, right? That's pretty powerful from the concept standpoint of getting things done. If I had the resources to support this, which I do in this cluster because I built this demonstration, kubectl scale deployment, hello world, 50 replicas, right? So imagine being able to just dynamically allocate 50 new copies of your web application in 1 line of code, right? An extremely powerful concept. kubectl get pods. We can see that those pods are in the process of all starting or getting started up. They'll start transitioning all into a running state in a few moments. So now I have 50 independent copies of my application running across all of the nodes in my cluster. And from a business standpoint, this is a huge deal, especially in the cloud. For years and years, I worked with customers to build web scale applications, and especially doing things like getting through bursts of like holiday seasons or marketing campaigns. And you're like, well, all right, well, I got to go provision 25 virtual machines, and I got to run a load test to make sure that I can actually support that workload. And that would take days, weeks, months to be able to do those kinds of things. Imagine being able to just add a couple compute nodes to your cluster, scale your application for the burst, and then scale your application back down, and then scale down the number of nodes in your cluster to reap those savings from a cloud standpoint. That's a very powerful construct to a business, and especially for you as practitioners in IT, to be able to respond to demands and workload quickly and easily. And there's a whole bunch of different tools and techniques to be able to even do that dynamically based on things like latency in your application. Oh, we're experiencing some latency. Let's start off some additional pods to support the workload. So that is an amazing piece of functionality. So again, we're going to get load balanced across all of the nodes, or excuse me, all of the pods running inside of our cluster. So as powerful as those things are, from a speed of deployment, I can also destroy things very quickly. And so just deleting the service and deleting the deployment will then start shutting down the application. So here you can see I did a delete service, delete deployment, and then I did a get all, which is going to list all of the resources in my cluster. You can see pods start changing to a terminating state. They'll start shutting down the applications, and a few minutes later, I'll be left with nothing but the individual service running inside of my clusters. Let me clear that, and then we'll run get all once more. And all that's left is running is the API service inside of the cluster. I'm going to leave this up to y'all to play with for fun, the imperative side of the house. But let's look at some code real quick. This, from this line 77 down, is the same exact demonstration as above, but with imperative code. So let's grab deployment hello world. So what we're doing here is defining deployment using an API object, right? So API version v1, kind is deployment. I give the deployment a name, hello world. So the same exact thing that we just looked at a few seconds ago. This pod template spec here is what I'm going to start up. I'm going to start up exactly 1 copy of my application. What application am I going to start? That's the application. So remember, we did a kubectl create deployment. We defined that image. we scaled it up to 3, and then we added a service. And so here we see a service listening on port 80, targeting port 8080. And so to deploy that, I could do bonus material, but I'll just go ahead and do it. When I roll that out, it's going to do that same thing inside of the cluster that we did just a few seconds ago to create the deployment and to create the service. If I need to scale that deployment, I literally can go here, I'll edit the file, I'll bump it up to 50 just for fun, save that out. Then I can reapply that file. So kubectl apply -f. It's going to go do all of the things in a file. You can see the deployment is configured. If I do a kubectl get pods, those are going to all start up again. So again, it's the same demo that we just saw a second ago, but all in code. So let's go ahead and kubectl delete -f deployment hello world YAML. So that's kind of the core constructs of how to roll out apps inside of Kubernetes. So let's jump back into the presentation and talk about one of my favorite topics, writing SQL Server in Kubernetes. So one of the interesting things about running containers inside of Kubernetes is a pod goes back to its initial state every time it's deployed. You might have worked with containers where you've done like a Docker run on your laptop and you have access to that container until you do a Docker RM and actually delete the container, and then it actually goes away. Well, because you can start and stop that container on your individual system. Kubernetes has to start and stop your containers across multiple systems. So when it stops a container that's running on inside of a pod on whatever node inside of the cluster, it's actually going to delete the container too. So when it comes back and creates a pod again, maybe I scaled my application back up or I made a change. Well, it's going to go back to the initial state of the container image again, right? So we have two things we have to solve here to deploy a stateful application like SQL Server inside of Kubernetes. We have to figure out state. Where do I actually store my data, right? Then I also have to figure out configuration. How do I configure my SQL Server if I'm going back to the initial state of my application every time, right? When I say the initial state, I mean literally the state of the container image that I'm deploying. Now, these might seem like really big challenges to overcome, but the opposite thing happens when I work with SQL Server inside of Kubernetes, because what we're able to do is decouple computation and data, right? Super powerful concept here. So same constructs that we have before. We have a cluster, I'll create a deployment, I'm going to expose it with a service. And so let's say I want to roll out SQL Server inside of Kubernetes, and I have a particular version of SQL Server that I want to roll out. Well, I'll create a deployment. That deployment creates a replica set, and that replica set is going to deploy that container inside of my cluster. So this is SQL V1, right? What we can also do, and I've talked about this in the beginning, is there API objects to allocate storage, right? So I can allocate storage to an application that's external to my cluster. I'll then expose my application to users over whatever network ports they might be used to. So in this case, 1433. So I'll send SQL Server traffic to the load balancer. It's going to get load balanced to the single SQL Server supporting that service, and users will get access to that data. And this is what I mean by decoupling computation and data. So that storage, that data is sitting on persistent storage somewhere in my data center, and I have a container that's attached to run SQL Server that's attached to that storage, presenting that data to the users. And it doesn't really matter so much where that container runs inside of my cluster, as long as I can send users to the load balancer to get access to the container, get access to the data. And you might have heard me say before, jokingly inside of presentations, nobody cares if SQL Server is online. What they care about is if they can get access to that data that's on persistent storage, right? That's the stuff that they really care about. And so what Kubernetes can do is, with the concepts of desired state, is I'll tell Kubernetes to do this thing, right? Create a service, start up a SQL Server container, and attach some storage. And I'll create databases and do whatever I need to do against that SQL Server that's running inside of that container. Well, Kubernetes provides a construct of a desired state. So what if this happens? What if the node dies? Or what if my application crashes, right? SQL Server never crashes, but let's be serious. What's going to happen is the cluster is going to realize that we're no longer in the desired state and start up a new container, maybe on a different node in the cluster, attach the storage, update the load balancer, and send users into the SQL Server container to get access to that data, right? So you get failover cluster-like functionality out of a cluster, out of a Kubernetes cluster, without having to deploy a failover cluster. Right? We do have to deploy a Kubernetes cluster, yes. There are some fine points about failover timing that we can geek out about after the session a little bit, but conceptually, this is what you're going to get for free out of a cluster. Let's say a new version of SQL Server comes out. Well, I'll update the container image just like I did in the previous example. What Kubernetes will do is use a technique where it's going to shut down the SQL Server instance first, start up a new SQL Server, and then attach that storage to the new version of SQL Server. Then load balancer is going to get updated, and I'll have access to that data almost instantaneously, right? Pretty cool stuff. So where does that storage live? That's kind of the next question, right? Because now I know I can run a pod anywhere on my cluster, but how do I get access to the storage to provide that to my applications? We have API objects to do that. We have what are called persistent volumes, which is the actual administrator defined storage, right? So that could be an iSCSI volume, an NFS volume, Fiber Channel 1, Azure disk, EBS disk, whatever it is. There's lots of constructs to provide abstractions around the physicalness of storage, get that available to the applications inside of your cluster. Your application is going to make what's called a persistent volume claim. So that's going to be an application level request for storage from the cluster. And there's a reason for that decoupling, which we'll talk about momentarily. That persistent volume claim is going to be how the pod or the application makes a claim of the cluster. So give me this type of storage, give me this much of this type of storage, then it's a responsibility of Kubernetes to go find that storage inside of the cluster. So your cluster administrators will provide persistent volumes, whether it be dynamically or statically. When I say dynamically, literally, you could just make storage appear out of a storage subsystem, or statically, where you'll actually have an administrator go and create a volume for you and attach that to your persistent volume claim. And the reason for this is the reason why there's this level of abstraction is the code that describes your application won't have infrastructure specific code in it, right? So when I describe my deployment, I'm going to say this deployment has this persistent volume claim, but what I don't want to have is maybe the actual implementation details of the persistent volume in the application's configuration. And we'll see this in code in a few minutes. It allows me to decouple those two things. So I can just give you a deployment manifest that says, I just need some type of storage, and then you go and provide that storage in your cluster so we can exchange those things easily. For SQL Server, let's talk about how we do that, or data persistency for SQL Server inside of Kubernetes. So we define persistent volumes and persistent volume claims, which is going to be the actual storage and then a request for storage. We'll attach those volumes to the default instance directory, which is var opt MSSQL. All SQL Server on Kubernetes deployments are on Linux, hence now you know why they put SQL Server on Linux. So at var opt MSSQL, you'll find things like the default data directories, your error logs, default trace, instance security, things like certificates will all be available at that location. And so what we're going to do is literally stick storage at that file system location. So as SQL Server changes and writes data, it's going to write that stuff to var opt MSSQL. That's going to pass through and go to the actual storage inside of our cluster. The default user database directory is a subdirectory of var opt MSSQL. So by default, if I stick a drive at that file system location via a mount, then all user databases will be created there. Of course, you can have multiple different types of storage attached to a pod if I needed to have different types of storage for different types of workloads. So that's the persistence and state side of the house. Let's talk about configuration now. We're going to inject configuration into our applications with environment variables. And they're going to be used at the startup of SQL Server to configure SQL Server that very first time. Remember, we're going to pull a container image, and it's going to be from Microsoft or from our own container registry, and it's going to have some sort of default configuration with it. I can then inject configuration specific to that exact deployment. So then kind of overriding what's occurring inside of the container for this specific deployment that I want to roll out. Of course, we have to accept the EULA because of reasons, and then SA passwords. This is the bare minimum that you need to start up a SQL Server container, is accept the EULA and then inject a password. And we'll talk about how passwords are exchanged inside of a cluster. Well, now, there's a Kubernetes object that allows you to store secrets. It's called a secret. It's not encrypted, it's hashed, and it's stored inside of the cluster, which means I can grab that secret and inject that into applications. And that's going to allow me to store that thing somewhat securely. There is a way to encrypt it if needed, or I can pull secrets from more advanced security constructs like secret stores and key vaults and things like that. But in our code demos here, we're going to do it dynamically at the command line. Yeah, the idea here is since the pod goes back to its initial state of the container image on creation, we have to inject these things, right? Now, what can you configure? Well, there's no SQL Server configuration manager in SQL Server on Linux. So if you think about all of the things that were available to you in SQL Server Configuration Manager to configure a Windows SQL Server instance, so things like what port is it running on internally, is it running a TLS certificate, is HADR enabled, all of those different types of things are surfaced as variables for you to inject configuration with. So it's not just these two. I think there's some 50 odd different configuration points that you can inject with environment variables. And so let's look at how we're going to bring all of that together in code to deploy SQL Server inside of a pod in YAML inside of our cluster. So now we're going to switch and focus mostly on declarative techniques. So what we have on the left here is I'm going to kind of walk through the YAML to deploy SQL Server. So we have an API version, which is a Kubernetes construct to kind of describe the specific versions of objects. So if we're going to do an apps v1 object of type or of kind deployment, so we're going to create a deployment named MSSQL deployment. Inside the pod template spec is going to be the number of replicas that we're going to run. We're going to run exactly one. And what that means is that's going to tell Kubernetes to just run exactly one copy of this application. If I need to run multiple copies of SQL Server, what I'm going to have is multiple deployments. So I have separate deployments for each SQL Server inside of my cluster. We're going to have an update strategy we've called recreate. Now, when you looked at the very first deployment that I did with the Hello World application, when I kind of stepped through it in the presentation, you notice that it started up some pods in V2 before it shut pods down in V1. That's called a rolling update for zero downtime updates. SQL Server can't really operate in that way because the data files behind the scenes have exclusive locks on them. So if I have the old SQL Server up and running and I use the default update strategy of rolling update, it's going to start up a new SQL Server. When I start up that new SQL Server, it's going to try to access those same files, which are going to have an exclusive lock by the first SQL Server. Going to shut down that first SQL Server, and then eventually the second SQL Server container will be able to get access to those pods. We don't want that to happen. So we define strategy type recreate. What's going to happen when I push out a new version of my app, I'm going to shut down the old one first and then start up the new one second. But it just takes a few seconds. So we'll see that in play in the demos here in a second. Inside the pod template spec, we want to tell SQL Server to have a specific host name. Otherwise, what it will do is use the name of the pod, which you saw at the end of the pod has a dynamically generated string when we deployed Hello World. Well, I don't want to have a dynamically generated string associated with the host name of my SQL Server. So here I can give it my actual SQL Server host name, a fixed host name that SQL Server will know about. This is important for things like monitoring systems or if you're configuring transactional replication, stuff that cares exactly what the host name looks like to SQL Server. For the longest time, the SQL Server container ran as root, which is a pretty bad security practice. So mid 2017 or 2019, they changed that so that it runs as a named user, not as root. And so let's dig into how we deploy SQL Server now. So inside the pod template spec, which is the section of the deployment that we're in right now, we're defining a container that we want to run, and we'll define the full path to the container register for the container image for SQL Server. So there we see 2019, CU9, Ubuntu 18.04, right? So that's the exact container image that'll get pulled to support this deployment. The SQL Server itself is running on port 1433. That's where we'll send traffic to. And then if I need to inject config, we'll define our environment variables to look like this. We'll give it a key or name, except EULA, and a value yes. And so that's a way for us to inject config. For the SA password side of the house, I don't want to store the SA password in the YAML that I'm going to give to you. So I can say that value from, read from the cluster's secret key store, the secret named MSSQL for a key and a value of SA password. And so that's going to read the value from the secret key store, then inject that value here at runtime. From a storage standpoint, I'm going to attach storage. So there we see the mount point of var opt MSSQL. So that's where I'm going to attach the disks that'll be provisioned for my cluster. And then which disks? Well, I'm going to attach a persistent volume claim. And so when I talk about decoupling configuration and state, really this is kind of the representation of all of that, right? The configuration is injected via environment variables. State is going to be stored in the persistent storage defined by the volumes and volume mounts. What you don't see here is anything specific to my environment, right? So I can give you this code and you can run this in your environment if you have the ability to create a password or create a secret, and you have the ability to service a persistent volume claim. And I'll talk about that plumbing in the demos now. So let's go ahead and look at how to deploy SQL Server in Kubernetes. So I'm going to start off by creating an environment variable password. with a password of something so strong, which meets the password requirements for SQL Server on Linux. If you create a simple password and things start crashing, like your pod never rolls out, it's probably due to the lack of password complexity. And I'll show you how to pull the logs in a few minutes that make that to troubleshoot that issue. So here I'm going to create a secret. kubectl create secret generic MSSQL from a literal string. So there's a key SA password and then the value, which is going to be the password that I define on line 8 here. So that's going to create the secret. I'm going to roll out some storage. And so my environment here, I have an NFS server that's backing up my storage. If I were to do this in the cloud, this could be an Azure disk, but I'm going to create a persistent volume. It's going to be of type NFS, and it's going to live on a server inside of my data center on my laptop, jokingly, my lab environment. And it's going to attach to a path of that location. And then I have a persistent volume claim here that is going to map my request to that storage right there. So let's roll that out. I don't want to focus too much on the implementation details of that. I want to focus kind of on the big picture concept. So basically all I'm doing is saying I have storage at this location in my data center, and my SQL Server deployment is going to attach to that storage. And so this is the code that we walked through in the presentation just a few minutes ago for a deployment, replica size 1, the recreate update strategy, which will become important in a few minutes. I actually, before we talked today, instead of CU9, I bumped up to CU13. Let's see how things go with that last minute change. But we're going to roll out a CU13 2019 container. I'm injecting an additional environment variable here to start our SQL Server agent. We're going to inject this configurations that we talked about during the presentation, except EULA equals yes, and that's a password. And it's going to read from that secret that we just created together. I'm going to attach my NFS to var optmsSQL. So conceptually, think about that as plugging a drive into that directory location or inside of the container. Let's go ahead and close all of that. We will roll out SQL Server. So run that code there. So looking at what I did here, I did a kubectl apply -f for storage, 1, 2, create it, kubectl apply -f, deployment create it, SQL Server create it, and I should have a SQL Server up and running. So here, MSSQL deployment is up and running. That literally is the power of Kubernetes. Again, just kind of showing off a little bit. I just rolled out a full-fledged copy of SQL Server inside of my cluster. So let's use the same techniques as we did earlier. I'm going to get the service. This time the service is running on port 1433, where a few minutes ago it was running on port 80. So let's load that into an environment variable and make sure we got everything. So I'm going to echo that out. So that's where my SQL Server service is living at that location. So I'm going to use SQL CMD to talk to that specific SQL Server on that service IP on that port. And I'm going to ask, hey, what's your name? What's your version, right? My name is SQL01. My version is RTM CU13, right? Again, I just rolled out a fully fledged SQL Server in like, what was that, 30 lines of code in a few seconds inside of my data center, right, on my laptop. Let's create a database. So use SQL CMD. I'm going to pass in a query, create database test DB1. So I created that database. And so now I want to drill home kind of the concepts of abstraction now inside of the data center. So I have a collection of nodes running in my cluster, kubectl get nodes. I have 3 nodes that support workload, 1, 2, 3. Though, and then kubectl get pods -o wide. My SQL Server is running on node 3, right? The storage associated with that is somewhere else in my data center. So I have an NFS server in my data center that is providing access to storage. This could be, again, remember we talked about iSCSI, this could be Fiber Channel, this could be Azure disks, whatever. But this node needs to have access to that storage. And then it can attach that storage and it's going to write the data to where that storage lives. And so on my storage server, which lives somewhere else in my data center, aka laptop, I have provision some storage, right? So I'm just doing a directory listing on the NFS export, which is kind of think of it like if you're, it's like a share in SMB or in Windows networking terms. And if I do a directory listing on the data directory on that storage server, there you can see all of the databases associated with the instance, right? So just a few minutes ago, I could do date right here. So 1851 UTC. So just a few minutes ago, it went ahead and created all of that storage. And then we have test DB1, which is created when I created that database. So that's where the stuff physically lives in the cluster. So if my pod fails on node 3, meaning that the pod dies or the node dies, well, it'll just start up on node 2. It'll attach that mount and have access to that storage again. SQL Server thinks that that stuff lives in VAROP MSSQL, even though it's physically living somewhere else. It's the responsibility of the container runtime to manage that mapping. And so it's a very powerful concept now, because now I just protect that data. And as long as I have SQL Server running somewhere in my cluster, I can get access to that data, right? So let's look at some failure scenarios now. Shutdown with no wait is a way to crash SQL Server ungracefully. Is that a term? Not gracefully. So shutdown with no wait. So I just crashed SQL Server. If I look at the deployment, what's going to happen is about 3.5 minutes ago, let's say 3.5 minutes ago, it created and started the SQL Server container. And about 10 seconds ago, when I ran that command, it was like, hey, SQL Server is not running. And it starts it right back up, right? So this kind of compresses the log entries because they're similar. But I know the first log entry was 3 minutes ago, and the second log entry was 10 seconds ago. Because the second I crash SQL Server, Kubernetes is like, nah, start another one back up. And if I scroll up here, we can see what happened is the state is currently running. The last state change was terminated because my application threw an error with a non-zero exit code, and it just automatically restarts my application. And we see restart count is incremented there. So if I do a kubectl get pods, you'll see the restart count incremented about a minute ago. And that's some of the value that Kubernetes provides, is because my app crashed. And it's like, that's cool. You told me to keep one up and running, right? The desired state, it went and started one back up again. And if I should be able to access my app, there I'm still running on CU13. What if I do something so silly as deleting a pod? So if I go ahead and do kubectl delete pod, that's going to delete that entire pod. That SQL Server is gone, right? A deployment creates a replica set that creates pods. I didn't delete the deployment, and I didn't delete the replica set. The replica set's like, you're supposed to have another pod up and running. And so what's going to happen is the replica set's going to realize that that's not in a desired state, and it's going to start up a new pod. So the previous pod, MSSQL deployment, ended in 2 HP. We can see the new pod ends in DXKK. It's up and running. It's been up for about 19 seconds. So you might be thinking, well, what about the data? The data is still there, right? If I ask SQL Server where its data is, well, it still thinks it's at VAROP MSSQL, but it's really on my NFS server. It just started the pod back up. Excuse me, let me be more precise. It created a new pod from the container image. My configuration is defined inside the manifest. My state is defined inside of the persistent storage. Start the pod up, send users to that pod. That pod's going to read the data from that location. My users have access to the data that they're expecting. Super powerful concept there. So we're going to update SQL Server here. Next, we're going to do a rollout. So kubectl set image. I'm going to change the image to CU14. So I'm going to go from 13 to 14 in this many lines of code. I like to make the joke here. If you've ever patched on a weekend, you know it's a lot harder than to patch a SQL Server, right? And so what's going to happen is the cluster is going to realize that I changed the container image, and I did it here imperatively. I certainly could have gone and changed the manifest from 13 to 14 in the code that we wrote out initially. We can see that the image is updated. If I look at the deployment, we can see the initial rollout of my app. When it's scaled from 0 to 1 for the initial pod, it's going to scale that pod down. It's going to shut it down first. Remember, recreate being the deployment method, and then create a new pod. And we should see now that I'm in a desired state on the new replica set that was created 43 seconds ago. Remember, there's two, right? There's the old replica set. Now the new replica set, the old replica set is scaled down. And I have my new SQL Server up and running. If I try to access it though, I got it too fast. When you do transition between cumulative updates, it's got to run the update scripts for the SQL Server engine. And so usually the point I try to make here is the pod might be up, but the SQL Server might not be available yet because it's running the upgrade scripts to go between the cumulative updates. But this time I missed it. I got it too late, and it finished the update scripts first. But if you look at the logs associated with that, you'll see that it went through and ran the update scripts that you would expect. And so to kind of cover a couple of points here, if something goes wrong, I talked about that in the beginning, maybe like your password's not working or something like that, or the container's not starting, you can use kubectl logs and then the name of the pod that you want. And so let's pop that down in the bottom here. I do a tab. If I do a pipe to more, so what we'll see is the actual SQL Server error log, right? Normally you go into SSMS, you pop open the error log, or you use the stored procedures to read it out. Well, this is that exact same content available to you via this command. So if something goes bump in the night with your pods and your pods are up and running, but SQL Server's not, then this is your go-to place to start troubleshooting what's happening. So we have two different versions of our app. The very, very first one that rolled out and the second one that rolled out. So CU13, I made a change, CU14. So that's the two rollouts. If I want to find out exactly what I'm looking for, I can use kubectl rollout history to get what the exact version of the deployment was on that first iteration. So here we can see CU13 is what was that very first rollout. I can roll back if I want to. So it's kubectl rollout undo deployment and roll back to the previous version. So that's going to shut down CU14, roll back to CU13, do the update scripts, and then off I'm going with my application on the previous version. So very powerful construct there. And that's why Kubernetes will keep that second replica set around. So kubectl get replica set. That's why it keeps the previous replica set around, because I can roll back to it if I need to. So what we're looking at here is the new replica set that I created 3 minutes ago is scaled down. The old replica set running CU13, which I created about 10 minutes ago, now has a pod that's up and running inside of it. So if I check the version of my app, I'm back on CU13. So again, think about the concepts of what's occurring here, right? I'm going to give you all the code to do this, but we wrote out SQL Server, created a database, we killed it, deleted it, came back every time. I went from 13 to 14, upgraded it in code, right? And just all declaratively in code in real time here, and then rolled back if I needed to. So super powerful concepts there. So why? Why SQL Server on Kubernetes? So Ben and I wrote a book, Ben Weissman and I wrote a book called Azure Arc Enabled Data Services. And honestly, the book's great, but the foreword to the book was written by Travis Wright, who's the principal program manager over Azure Arc Enabled Data Services. And in the foreword to that book, Travis describes the journey of why they put SQL Server on Linux. And it wasn't to put SQL Server on Linux. It was to get to this end game here, Azure Arc Enabled Data Services. And so what he describes is the engineering story of how to take SQL Server, put it on Linux, put it into a container, put it into Kubernetes, and all the while providing tooling for this. So that's why Azure Data Studio came about, right? Because I needed to have cross-platform tooling. So now I have SQL Server and Kubernetes. What am I going to do with that? Well, I'm going to build Azure Arc Enabled Data Services to build a hybrid cloud deployments of Azure wherever you have compute, right? And we talked about that in the beginning. Concepts of Kubernetes, just I have an API that gives me access to a collection of resources, right? Compute, network, storage. And so if I run SQL Server on Kubernetes, I can run it anywhere. I have compute, whether it's in Azure or in AWS or in your own data center. Take the concepts of Azure with identity management, log management, role-based access control, all the goodness that Azure brings to the table, manage backups, things like that. I can now take Kubernetes and put that anywhere. And then I can run Azure services on top of that, wherever I want, right? So SQL Server goes inside of a container, right? I can run SQL Server wherever I want. Now we can run Azure services wherever we have Kubernetes, bringing that whole story together inside of Azure Arc Enabled Data Services. And I love this slide because the first bullet point on the left, have Kubernetes in your infrastructure. You have Kubernetes, then you get all of these things on the right. You have the ability to deploy Postgres Hyperscale on-prem, Azure SQL Database on-prem, Azure, or say hybrid cloud, to be most precise. So it can be any cloud or on-prem. Azure SQL Database with high availability and managed backup. All the governance and all the compliance that comes with Azure is extended to your data center. If you look at the bottom here, we see on the chart, we see Kubernetes and a collection of nodes, persistent storage, all the concepts that we're talking about today. And the idea is Microsoft is going to write the code that describes what Azure Arc Enabled Data Services is, right? And you take that code and you deploy it wherever you have Kubernetes. And so all those concepts of persistent state, access to networking, all come together to make this thing, right? So really cool stuff. So I think we covered a whole big bunch of stuff in the last hour. Like what is Kubernetes, right? It starts containers on nodes in a cluster. The benefits, obviously, looking at how we were able to roll out applications and scale applications and update applications, leveraging Kubernetes is super powerful concepts. The API objects are the constructs to build these things. So pods, right? Controllers like deployments, persistent volumes for storage, services for access. We looked a little bit at the architecture and we deployed a stateless app, Hello World. I deploy Hello World at cloud scale. And then also SQL Server, right? Tons and tons of resources available to you. So again, Ben and I wrote a book on SQL Server and Kubernetes in addition to the Azure Arc enabled book that I was talking about a second ago. You can get a deeper dive. You can build your own clusters, the whole 9 yards available in that book. I showed you in the first demo that if you have Docker today, you're a mouse click away from running Kubernetes on your desktop, right? All the managed service providers like AKS, EKS, and GKE provide managed Kubernetes. Almost all of them are for free. I know Azure has a free subscription, and those are all links to the kind of the 101 documents of deploying a cluster and then deploying an application into the cluster. I've had the luxury of the last 5 years of being a Pluralsight author. I've written 23 courses now, a bunch on Kubernetes, a bunch on Linux, a bunch on Azure. Go check out that content there. If you want access to that content for free at Pluralsight, shoot me an email. And I'll be happy to give you a free trial code to get access to that content. This is not a sales pitch, but if you want to get into that stuff and learn a little bit more, please let me know. I'm all about spreading the love there. So there's my contact information. I blog a whole bunch. There's the GitHub repo that I'm going to put this presentation up to in a few minutes, and all of the code available to y'all. So I'm going to go ahead and open it up for questions.
Perfect. Thank you very much. So, Mikhail, do you want to jump to the first question?
Yes. The self-healing functionality requires multiple versions of the same pod/application. Do the pods do load balancing even between clusters, or can we have distributed clusters somehow so that the pods aren't created in the same physical environment?
So let me repeat back what I think I heard. So within a cluster, a load balancer service will load balance within a cluster. One of the common patterns is, especially if you look at like the Azure, that's kind of the majority of my experience with this type of topology is going to be in Azure. You can use Azure Traffic Manager as an overlay to distribute traffic to multiple clusters, or things like App Gateway to receive traffic and distribute it to your cluster. So you can kind of get like meta load balancing above that, right? So to go across to Microsoft's got a bunch of design patterns for DR scenarios, especially for things like stateful applications, but also for stateless applications for distributed workload. That's a good question.
Great. So do I need to use Docker containers in order to use Kubernetes? And what is this I keep hearing about Docker no longer being needed?
I love this question. Cool. All right. So the big thing about that is, be very precise about how I say this. Docker is tooling. Docker is most effectively creates containers, but it also runs containers, right? If you look at the architecture of Docker today, Docker actually doesn't start containers. Docker tells a thing called container D to start containers. Container D is a wrapper around another element called runc, and runc is what actually communicates with the base operating system to create the container. So you think about all those layers: Docker, container, runc, the actual kernel, the OS, right? What the deprecation of Docker and Kubernetes did is just took out the Docker layer, right? So inside of Kubernetes, inside of the cluster, you'll still run container D. You just don't have the tooling or the wrapper that is Docker around that inside of the cluster. And that was an architectural shift about 3 or 4 years ago to put Docker to communicate to container D. Inside of a Kubernetes cluster, you don't need things like creating an image or building an image because you're deploying created images inside of Kubernetes. So you don't really have that need inside of a cluster. So you can take a Docker image that you built on your laptop and push it into Docker Hub or whatever container registry, and Kubernetes running container D will be able to pull that image down because that image format is a standard. There's no nothing special about a Docker image or a container D image. They're the same thing. I forget the actual abbreviation, but the OCI, I think, is what it is the container image standard. So that's kind of the way I break it down. Is Docker creates images today, but you use container D to run the images. You just happen to use Docker to start container D wherever you are, right? And let me show you one thing I think it'd be cool to see if we're asking those kind of questions. So I'm just creating a quick deployment. The very, very first demo that I did, kubectl get pods -o wide tells me where it's running, right? Kubernetes has one job. starting pods and clusters. That pod is a container running on C1 node 2. If I SSH into C1 node 2, so that's the actual computer in my cluster that's running on. If I do a PS minus EUX pipe more, that's going to give me all of the processes running on this particular Linux node in my cluster. And if I go down to, let me add minus forest. Where is it? Where is it? So this is the actual process that's running my application right here, right? So container D starts the process or starts the container that's just my hello world application. If this was Docker, you would literally see a parent process to this container D process. It would be Docker, start a container D, and then start up my app hello world. And that's what pretty much what that deprecation of Docker really did. It just removed the tooling from the equation, and we still just have access to container D. So I know that was kind of a long-winded answer to the question, but that's a very, very common question.
So final question then is, since it's possible to create SQL Server database files on shared storage, such as file shares or even cloud blobs, would this be a bad idea for our Kubernetes deployment? And should we always use the pre-configured Kubernetes persistent storage?
So the dependency of the performance of storage doesn't change in Kubernetes. So for years and years and years as DBAs, I work for a storage company now too. We made sure our storage had to be rocket fast because of reasons, right? I need to have sub-millisecond, low latency, high throughput access to my data if that was what was needed. And so we still have to do that calculus when we're deploying inside of Kubernetes, but the physical constructs of that get abstracted away from the deployment. And so what you'll wind up doing is having different classes of storage in your cluster to deploy from. And we might have been trying to do this for years inside of our VMware environments. Like we have the gold tier and the silver tier, and then maybe like the long-term storage tier that's got maybe still has spinning disks, right? But you take those concepts and apply that into what we're doing in the cloud or in Kubernetes, and you still have to do those things, right? So those persistent volumes are going to be allocated from some sort of class storage inside of the cluster. And so what you'll use is you use the PVC, the persistent volume claim, to make a request of the type of class that you want. And you still have to manage that for those latency sensitive applications. You still have to figure that out. If you can use, like an Azure disk, which is stored in blob, and you're okay with the latency and the throughput constraints of Azure disk, then go for it, right? So you still have to do that math as a DBA on where your data physically lives and making sure that the SQL Server process that's running on the node, if it's got to have low latency access to the storage, well, those have to be physically adjacent with high throughput, low latency connectivity. And that's still is a thing to account for. How you deploy though is a lot. I'm trying to think of the right word. More abstract because you're just writing code to do those things, right?
Great stuff. All right, thank you very much for that.
That would be the last of our questions for now.
Cool.
Thanks to everybody for joining us, and a big thanks to Anthony.
Thanks for having me, team. I appreciate y'all.